Okay, on page 43 today, and our last topic for this unit is something called residuals. We a little bit introduced this idea back when we were looking at creating models for functions. We had one problem where we looked at what's the difference between our predicted value and the actual table value that we had. That's the idea that we're going to talk about today in a little more depth. So the first example that I have says a skydiver jumps from an airplane and an attached microcomputer records the time and speed of the diver for the first 12 seconds of his freefall. And we have that data listed for us in this table. The very first thing we're going to do is create a model for this information, the same way we did before. So I'm going to open up my calculator. I'm going to make a spreadsheet, and I'm going to recreate this table in my spreadsheet. So I'm going to grab my calculator here. And I want a list and spreadsheet. I'm going to call the time my X, and I'm going to call the speed my Y. So time are those X values and the speed is my Y. Now, be careful when you enter your values. I believe we talked about this yesterday. I was going through this problem a little bit earlier today and had made an error typing in my values. And I was, why is everything all crazy? This isn't a function I was supposed to get. It's because I had mistyped something. So just make sure you're really careful entering your values. So my time values are 2, 4, 6, 8, 10, and 12. And then I'm going to enter those speed values. Okay, and then again, don't forget to enter after you type in that last value. So I have just recreated the table that was on my paper in my calculator. Again, I called time the X and speed the Y. Now I want to find an equation for a line of best fit. Since it says a line, I know when I go to find that regression here in just a second, I'm going to select the Y equals MX plus B format, a linear format. Since it says line, I want to use linear. So I'm going to go ahead and do Control Doc to add a page here. And I want to add a data and statistics page. And we've done this already. So this should look familiar. Assign your variables, X where the X axis should go, and Y where the Y axis should go. And there's my scatter plot. Okay, here's my scatter plot. Now it says line of best fit. If you're looking at this and thinking, I think a curve might fit a little better here, I would agree with you, but it says a line of best fit, so we'll find a line. I'm going to go to Menu, down to Analyze, and then Regression, and I'm going to choose the MX plus B option. Okay, there's my regression equation. And it says to round my coefficients to the nearest tenth, so that's what I'll do here. So that would be 6.0x plus 13.1. Okay, so I will go ahead and put my calculator away for just a second so I can jot that down in my notes. Write down my equation here. Y equals 6.0x plus 13.1. And then it also asks me to characterize the correlations of this data as strong, moderate, or weak, as well as positive or negative. It was a pretty decent association there. I definitely, when I looked at my line, definitely had a positive slope. So I'm going to call this a strong and positive. There was definitely a trend to my data. It wasn't spread far apart. So that's where the strong is going to come from. And then positive because my line that we got there had a positive slope. Okay. Now what we're going to do is use this model that we found and determine what we would expect our predicted values to be based on the model. So if this perfectly followed the line that we found, what would those values be? I know what they actually were, but if it perfectly followed the model, what would those values be? That's what we're going to find here from our prediction. So this is a prediction based on the model. So what I'm going to do is plug in this value for X to my function and see what I get for Y. So if I were to plug in 0 for x, I would get 13.1. Does that make sense? Okay. If I were to plug in 2 for x, I would have 6 times 2, that's 12, plus 13.1 would give me 25.1. And then I'm going to do the same thing for each of these values. I'm plugging them all in for x and recording them in my table. Okay. Now I've done this already. What I don't want to spend the bulk of our time on today is plugging values into x for a linear function. I know that you guys can do that. So instead, I'm going to jot down the values that we get here because I want to spend our time somewhere else for today, not with plugging in values for x. So if I were to plug in, which I did plug in, all of these values for x into our function, this is what we would get. You with me? If I plugged in 8 for x here, 6 times 8 is 48, plus 13.1 gives me 61.1. Okay, that's where all those numbers came from. I plugged this value in for x in my function. Now our new idea for today, because plugging values into a linear equation is not a new idea. Our new idea for today is this idea of a residual. So the idea behind a residual is it's the difference between my actual value, my recorded data, versus the prediction I get from my model. Okay, so the next thing we're gonna do is fill in the residual line for our table here. So this is our actual table value minus the predicted from our model. Predicted, there we go. Actual minus predicted, okay? So I would take this minus this. So 0 minus 13.1 is negative 13.1. 25 minus 25.1 would be negative 0.1. That make sense? Okay, so I'm gonna keep doing this. 46 minus 37.1, that would give me 8.9. 60 minus 49.1, that would give me 10.9. 68 minus 61.1, 6.9. 72 minus 73.1, that'd be negative 1.1 since the predicted is greater than the actual here. And then my last one would also be negative since the predicted is greater than the actual. So 74 minus 85.1 would be negative 11.1. So these are my residuals. The residual, again, is the difference between my actual observed data and the prediction from the model, okay? The next thing we're gonna look at is a plot of our residuals. We care about these residuals because they tell us if our model is actually a good fit for our data or not, okay? So we're gonna make a little graph of our residuals. My graph will be my residual versus my time. So the actual x value. So what I'm gonna plot here is the residual for each x value. And then I'm gonna do my residuals by 5s. I'm just trying to pick something that fits decently in the space I have here on my paper. And then I will do my x values by 1s. And we only go to 12, so that's far enough. Okay, so when my time is 0, my residual is negative 13.1. So that would be here-ish. When my time is 2, my residual is negative 0.1. So I'm just barely under that line. When my time is 4, my residual is positive 8.9. So I'm just under the 10. For 6, we're at 10.9, so we're just above the 10. For 8 would be here. We're at 6.9, so we're a little above the 5. For 10, we're at negative 1.1, so just down here. And for 12, which would be here, we're at negative 11.1, so we're a little under the 10. There's my residual plot, okay? I plotted, again, the time versus the residual. Can you see that there's a shape here? Got like an arc to it. It almost kind of looks like a parabola, right? I'm going to go over it with a color so we can see that there. So we've got sort of this shape to our residual. That is exactly what we do not want out of a residual graph, okay? Having a pattern to our residual, having this shape to our residual, again, is what we do not want. And that's here in D. We do not want residuals to fall along a curve or make a distinct pattern. Okay. So in this case, that linear model that we picked is not going to be a good representation for what's happening here. My residual graph should be like random and sporadic. There shouldn't be a pattern to it. I should have some stuff above, some stuff below. If I have a pattern to it, then that means the model I picked, I can predict when it's going to under predict or over predict. Okay, I shouldn't be able to do that. A good model is going to have some stuff above, some stuff probably below. I shouldn't have everything above or everything below because then my model isn't good again. But if I've got this sort of pattern to it, okay, if I can make a distinct pattern out of my residual graph, that model that I picked is not a good fit. So since we've got a distinct pattern here, that means that our linear model is not a good fit. Let's scoot this up a little bit. The residuals do show a distinct pattern. So the linear model is not a good fit for the data. I want to show you a couple of things on your calculator really quickly. The big idea that I want you to take away from today, though, is if you look at something that is called a residual graph, you should not be able to find a pattern, okay? It should look kind of random. So let me pull up my calculator here. And I want to show you a couple things. One, your calculator can give you a residual graph. So if it's not provided to you, it's not already on your paper, and I'm not asking you to create it by hand, you can do it on your calculator. So I'm going to go to menu from my scatter plot page. And once I already have my best fit line there, if you don't have the model, then it doesn't make sense to look at a residual because there's no model that you're comparing to. But if we go down to analyze, and regression is where we found the model. Right under that is residuals. There's a couple different options here. I'm going to show you the residual plot since that's what we looked at. Okay, that's down here. This is exactly what we plotted on our own paper. Residuals versus our X values, and we got that same shape. Okay, since I've got a predictable pattern here, that tells me that my linear model is not a good fit. Now let me put that residual plot away. And then if we think this linear is not a good fit, because we've got a curve to this data, remember that in your sort of menu of regressions, you have a lot of different options. So maybe this is going to look like an upside down parabola and it's actually quadratic, or a parabola, I should say, with a negative lead coefficient. Maybe this is actually something exponential. But I have a lot of different options. And if I wanted to try something, I could probably first get rid of hide linear. We'll do quadratic just to see. So I wanted to try something different. We could pick a different model and see if maybe that fits my data a little bit better. Okay, so you can test this stuff out with your calculator. You can also get that residuals plot with your calculator. Let's take a look at another example of a residual graph. So turn the page for me. And this time we've got the scatter plot with that best fit line already on our paper. Okay. And so for this next example, we're not going to algebraically find those differences. We're going to find them on the graph. There's going to be a little estimating here. That's okay. So we've got our points here, our scatter plot, and then our best fit line here. So in this context here is that a school district was attempting to correlate the number of hours a student studies in a given week with their grade point average. They surveyed 8 students and found the following data. Now, since we're in the statistics unit, and one of the things we talked about earlier was sampling, good sampling methods, unless the school district is like 10 kids total, only surveying 8 kids is not a good sample. Okay, very, very tiny. We talked about this with that rubber ducky factory problem, right? Ernie, he only checked like 10 ducks out of 100,000. So this is not a very good sample, but we're gonna use it to look at this residual graph anyway. But we've got this sort of line of best fit that we have plotted in here. And what we're gonna look at is, again, the difference between my predicted value and my actual value. Now, the first question talks about, is this a strong, moderate, weak correlation, positive versus negative? Our data isn't quite as tightly grouped in that same pattern that we saw last time. Last time our data followed a pretty strong curve. Here we're a little more sporadic, so I would say this is maybe a moderate correlation, but definitely positive. And now we're going to use our scatter plot here to calculate our residuals. We're going to do it right on the graph. So what I'm looking for is, again, what's the difference between my actual value and my predicted value? Okay, so the difference between my actual value and my predicted. So that means this minus this. Anytime we're below, the point is below the line, that's going to be negative. So this is negative. If I look at the scale here, there's 75 and 80. So each of these chunks would be 1. So I'm going to say 1.5. For here, boy, we're almost right there. I'm going to say that would be positive 0.1. We're just barely above. Down here, this is maybe a half below, so minus 0.5. For our next point, we're pretty far off. So this is 1, 2, maybe 3 about below, maybe 3.1. For our next point, we're above, so this will be positive 1, 2, 3, 4.5. I'll say there's some estimating here. If you're choosing values slightly off of mine, that's okay. If you said this was negative 3.1, that's okay. And then here we're below, so this would be negative 2 about. And then for our last point, we're above, so this would be positive. And 1, 2, 3, 4, 5.5. So there are my residuals from the graph. Again, notice anytime the point was below the line, our residual is negative. Anytime our point was above the line, that residual is positive. Okay, how far is my point below or above the line? That's what we're looking at there. And now we are going to make a sketch of that residual plot. Okay, I want to know if this model is good or not. My initial reaction to this line is it seems to fit these points pretty well. I don't know if we're really on the ball when we get farther out. I don't know. So that's why we're going to look at the residual plot. So I'm going to make a little sketch here of my residuals. Same idea as before. And we're not nearly as spread out as we were before with our residuals. So that should make this hopefully a little easier. Okay, so remember this is our residual, sort of along that y-axis. And then our x value was our studying. And again, that was our x value from the original graph. So I'm going to go by ones for the x-axis since this goes by ones. 1, 2, 3, 4, 5. And we need to go up to 11 here. There we go. And then for my residuals, I'm going to go by ones. So I've got my residual plot set up. And now I'm going to plot those differences I marked on my graph. So when our x value is 2, our residual is negative 1.5. So at 2, we're at negative 1.5. At 3, we're at 0.1, so just above there. At 5, we're at negative 0.5, right? Our x value is 5, we're at negative 0.5, so 5, negative 0.5. At 7, that would be here, we're at negative 3, so 1, 2, 3. At 8, we're at positive 4.5, that'd be about there. At 9, we're at negative 2, so here's 9, 1, 2. And then at 11, we're at positive 5.5, so 6. 5.5 would be here-ish. There's our residual graph. Do we see the same kind of pattern in this residual graph that we saw for the last example? No, I don't have a strong pattern or a curve here, right? I've got some points that fall below, some points that fall above that horizontal axis that I have here. It's sort of all over the place, right? That's what I want to see from a residual graph. This means I have a good model, okay? So does the residual plot indicate that a linear model is appropriate? Yes, there's no pattern. There is no pattern on the residual plot. So the linear model is a good fit. No pattern here. And it's not even one above, one below, one above, one below. It doesn't even do that, right? I've got a couple below, maybe one above, maybe another one below, a couple above. No predictable pattern here. That's what I like to see in a residual plot. Questions for me so far? Okay, we've got just a couple more examples we're going to take a look at. Turn to the last page in your notes packet, page 45. Okay, you don't have to sketch any more residual graphs for today. They're provided to you. So let's take a look for 1 and 2 at the residual plots that we have and determine which of them indicates a good fit and which of them does not. So for number 1, it says, which of the following residual plots would indicate that the linear model is appropriate? So remember, I want a residual plot that has no pattern, no predictable pattern to it. So which of these tells me that I have a good model? Which of these residual plots tells me I have a good model? 2, yeah. That has a pattern, that has a pattern, this has a pattern. 2's got no pattern. 2 is chaos. That's what we like out of our residual graphs. Now, number 2, opposite question. Which of the following residual plots would indicate that the linear model used to produce it was an inappropriate choice? So which of these residual plots is bad? 4, yeah, I do not like 4. These are all crazy. Good, that's what I like out of residual plots. This guy, pattern, no, thank you. With me so far? Okay, residual, hot mess, good, predictable pattern, bad. Okay. For example 3, it says a set of data is given right here. The equation for the line of best fit is this. I didn't even have to find the line on this one. They gave it to me. Which of the following represents the value of the residual for the data point where x equals 10? I have the actual data point when x equals 10. So we need to find the predicted. So I'm going to plug in 10 here. So 5.2 times 10 plus 18. This would give me 52 plus 18, which would be 70. Okay, so my predicted here would be 70. Actual minus predicted, right? 62 minus 70 would give me -8. So my residual when x is 10 would be -8.
Why do you have to subtract 70 minus 62?
It's always the actual value minus the predicted. So whatever y I have from my collected data, it's always going to be that minus whatever I got from the poll.
Okay.
Does that make sense? Okay. Okay, and then last example here. For how many points in the graph is the number of cars washed predicted by the line of best fit less than the actual number of cars? So I want the line to be less than the actual. Okay. So that would be right here, right here, right here. The line is below the actual value. 1, 2, 3. Not too bad. I know making the residual plot by hand is a little tedious. The stuff we did to get there, not so bad, right? And then these are the types of questions, stuff like this, maybe a question about find the residual. That's the kind of stuff that you can expect to see on an SAT question about residuals. And this stuff, not so bad, okay? So that's it for residuals. Again, the big thing I want you to remember is that when I look at a residual plot, if it's a mess, if there's points everywhere, utter chaos, no pattern, nothing predictable, I have a good model. If I have any sort of pattern to my residual plot, it's not a good model. I need to pick something else.